No zeros, or 1. 10 to the 1 is 1 with 1 0, or 10. 10 to the 2 is 100, and so on. Now, for very small numbers, you use negative exponents. So 10 to the minus 1 is like 1 over 10 to the first, or 1/10. 10 to the minus 2 is like 1 over 10 to the 2, or 1/100, and so on. Now, the other thing we have to know is the unit of distance in astronomy, which is called the light year, which is 5.88 trillion miles. Or, for those of you who prefer metric, 9.56 trillion kilometers. A light year is not a unit of time, as they like to put into science fiction TV shows. The other thing you need to know is scientists tell temperature in a unit called a degree Kelvin, or a Kelvin. That's the same as the centigrade degree, but starting at absolute zero, which is minus 273 degrees in centigrade, or, for those on the American system, minus 459 Kelvin. Or excuse me, minus 459 Fahrenheit.
You should mention that the light year is the distance that light travels.
In 1 year. Yes. For those who didn't hear, light year is the distance light travels in 1 year. For perspective, the sun, at 93 million miles away, is 8 light minutes. So, we're talking about some big distances here. Okay. So, the events detailed in this talk were derived from a combination of astronomical observations, calculation based on experiments in nuclear and particle physics, and the theory of general relativity. This has led to a model that is consistent with observation of the both very large and very small. That said, many of the fine details are still under contention. There's still a lot of physicists calling each other idiots in the literature over this. Politely, of course. Because of time constraints, I will skip over details on the history of the discoveries and when the calculations were done. But for those who are interested, I do have a bibliography. Okay, current research indicates that the universe began 13.7 billion years ago in a cataclysmic event called the Big Bang. It is not known what existed beforehand or why the event occurred when it did. Also, we are only able to calculate back to a certain point in time before which our knowledge of physics breaks down. In the beginning, that's the only biblical reference, though. The universe was contained in a near single point of near infinite density called the singularity. And then, for unknown reasons, it went boom and started expanding. Now, at 10 to the minus 50 seconds, remember, very small numbers, the universe was at a temperature of 10 to the 35 kelvins. At that point, the 4 known physical forces were all mushed together into one force. The 4 forces are electromagnetism, which is light, electricity, magnetism. The weak force, which is an obscure force that controls the decay of subatomic particles like neutrons. The strong force, which is the force that holds nuclei together. And the gravitational force, which of course is the force that keeps us on the floor. So anyway, then at 10 to the minus 42 seconds, the universe had cooled to only 10 to the 32 kelvins. At that point, the forces of gravity separated from the other 3. In physics, this is known as breaking a symmetry. But basically now gravity became its own force, and the other 3 were still mushed together. Then at about 10 to the minus 37 seconds, it entered what's called the supercooled state. Now you can understand supercooled as if you have a glass of water and you put it in the freezer and slowly cool it down, it will actually go below freezing temperature and remain a liquid until you bump it. And then that will cause the first ice crystal to form and it will freeze. Well, the universe was kind of in that state. It was supercooled where It was ready to form what was called a vacuum, but nothing had jostled it yet. So it stayed in this, what's called a false vacuum. Now what this led to is a period of super fast expansion called inflation, even worse than during the Nixon era. In fact, in 10 to the 35 seconds, 10 to the minus 35 seconds, 10 to the minus 35 seconds, the universe grew by a factor of 10 to the 30, from 10 to the minus 30 meters in diameter to 1 meter in diameter. This expansion caused the energy density in the universe to drop until space was able to go through the true phase transition into a true vacuum. The energy released by this phase transition created all the particles in the universe. Since, as according to Einstein, E equals mc squared, energy and matter are interchangeable. Okay. However, in order for the structures we see, the stars and galaxies, we need some variation in the concentration of matter. At this point, the universe was extremely uniform and smooth. So it turns out, let's have the right page. Turns out that these were caused by random variations in the rate of inflation at different points in the universe, which caused the inflation to end at slightly different times. Where the inflation ended later, matter was slightly denser than where it ended earlier. These differences had a difference of only 1 part in 10,000, but that was enough to create all the structure that we see. Now, inflation has an intriguing implication. The portion of the universe that we can observe is limited by the light distance can travel in the time since it's existed, somewhere between 10 to 20 billion light years. Now, prior to inflation, the universe was small enough that light could travel across the entire universe faster than the universe was expanding. But during inflation, it expanded faster than light could travel. So it's very possible, in fact very likely, that we only see a tiny fraction of the universe. In fact, possibly only 10 to the 23rd of what the universe really is. But 10 to the minus 20, well, we see 10 to the minus 23rd of the universe. So, now there's another version of interpretation which says that inflation has actually never stopped. But what happens is that every time a pocket in the universe expands enough to go through the phase transition into normal vacuum, a universe forms, but the bigger universe is continuing to inflate. So we may just be one little pocket of universe in a still inflating hyper-universe. I know this gets a little metaphysical, and there is actually no way we can actually determine if that's true. There's no measurement we can make, so it's all hypothetical. At least we scientists admit that. Okay. Now, the universe is continuing to expand, although inflation is over. At 10 to the minus 34 seconds, the universe is cooled to 10 to the 27 kelvins, and now the nuclear force, separated out from the other forces. And at this point, subatomic particles were able to form. But it was much too hot for any particle to be stable. What you had was what's called a soup of quarks and a particle called leptons. Leptons are particles like electrons and neutrinos. And then, of course, photons, which is radiation. Then at 10 to the minus, now things slow down a little. At 10 to the minus 10 seconds, at 10 to the 15 kelvins, now the weakened electromagnetic force is separated out. So now all forces are distinct. Now at 10 to the minus 6 seconds, when the universe cooled to 10 to the minus 13 K, now nuclear particles could form. So the neutrons and protons could form, but it was still way too hot for nuclei to condense.
We should capitulate that all of this has happened in less than 1 second.
That's why I said we're still at 10 to the minus a millionth of a second still. So this is pretty quick. Now at 0.1 second, things are slowing down a bit. 0.1 second, a tenth of a second, the universe cooled to only 31.5 billion degrees. At that point, the universe became thin enough that neutrinos could stop interacting with other particles. Now I should explain, a neutrino is a particle that is released when neutrons decay. It is extremely non-interactive. In fact, a calculation I had to do back in my astrophysics class in college, came up with an average neutrino can go through 3,500 light years of 3,500 light years of rock without hitting anything.
It's
So-
constantly streaming the sun through us, I think.
Yes, and we have these huge neutrino detectors buried deep underground, and we catch maybe 1 in 10 to the minus 30 of those neutrinos that are coming through.
1 in 10.
1 in 10 to the 30. Thank you.
You have enough water in there.
It's good to have some other sense. It's good to have some other. It's good to have some other scientists to keep me honest. Okay. The other particles, however, continue to interact rather vigorously, combining, forming new particles, annihilating each other, and just generally making a big confused mess.
The universe was opaque at that time.
Yeah, well, I'm getting to that. Let me proceed. I'll get to that. Now, by 1 second, the temperature fell to only 10 billion kelvins. At this point, the energy dropped low enough for electrons and positrons to stop annihilating each other. But that process, it took a while for the electron count to really settle down, and it took about 30 seconds. So now the universe is getting pretty old. Now, it's at this point also that the universe cooled enough for the nuclear particles, the protons and neutrons, to become stable. So they stopped forming and annihilating each other. But it was still much too hot for nuclei. Okay. Now, it should be pointed out that it's still not understood why our universe consists of protons and electrons and not antiprotons and anti-electrons. However, calculations also show that of all the particles that existed at the very beginning, it would only require 1 extra particle of regular matter out of 300 million total particles in order to get the current amount of regular matter. So in a sense, the fact that we're made of matter instead of antimatter is almost just a statistical variation. Okay, now things really slow down. At 1 minute, the temperature dropped below 1 billion Kelvin. At that point, nuclei could finally form. But only the lightest elements formed. Hydrogen at 75% of the matter, helium at 25%, and deuterium at 0.03%.
Is that still true?
I'm getting to that.
Not still true. Not still true.
I'm getting to that. Patience. We've got billions of years left. Or as Jonas Salk would say, billions and billions. Okay, now by 300,000 years old, the universe had expanded to 90 million light years and cooled to 4,000 kelvins, cool enough for the electrons to finally combine with the nuclei to form complete atoms. Now at this point, the photons would stop interaction with the charged particles, and the universe became transparent. This is known as decoupling. This process continued for about another 1 million years. Now, the remnants of this decoupling period are seen in what's called the 2.7 Kelvin microwave background radiation that is observed to come in all directions. Now, as the universe expanded, the temperature, as I said, decoupling occurred at 4,000 kelvins. But the background radiation now is only 2.7 kelvins. The reason is that as the universe expanded, like any gas expanding, it cooled. So now the temperature is down to 2.7 kelvins. And as the universe continues to expand, that temperature will continue to drop. Now, recent, very precise satellite measurements have detected variations of 1 part in 100,000 in the temperature of this background. This is very important because it provides the evidence of the small variations in density that then led to the complex structure that we now see in the universe. Now, some of you scientists may ask, doesn't the creation of the universe violate the law of conservation of energy? The law that matter and energy can either be created or destroyed. Now, the answer to this is that the gravitational energy actually is a negative energy. We have all this matter, which is positive energy. We have gravity, which is trying to suck it all back in, which is a negative energy. And it turns out the energy contained in the matter and the energy contained in the gravitational force cancel out. So the total energy of the universe is 0. So we're okay. Now, it should also be mentioned at this point that visible matter appears to constitute only 10% of the total matter in the universe. The remaining 90% consists of a mysterious form of dark matter that can only be detected because of its gravitational influence on the visible matter. Indeed, because it's 90% of the matter, it controls the dynamics of galaxy formation and motion. And galaxies are actually about 10 times bigger than they appear to be, with this huge halo of dark matter. Now, as mentioned previously, there were small variations in the density of matter after inflation. Once decoupling occurred, the attractive force of gravity became greater than the repulsive force due to the pressure of the photons bumping into everything. Therefore, the slightly denser regions started to attract surrounding material into them and started to form galaxies. This collapse was not uniform amount of time. Because of the irregularities, galaxies would tend to collapse more in one direction than in the other. This led to galaxies becoming, the gas clouds being flattened, and led to so many of the galaxies being in a spiral shape. Because some matter would fall in faster one way than the other, and you wind up with a flat structure. Now, also, the interactions between the gas molecules as they collapse would cause turbulence, which would cause heating. This in turn would have caused more turbulence, which would cause the clouds to break up into smaller and smaller clouds. As this progressed, they could separate out into galaxies, and then inside the galaxies, they could break up into stars. Now, what also happened is the galaxies would form clusters of galaxies, and there's a great deal of evidence that the clusters of galaxies form clusters of clusters called superclusters. Now, the universe still being relatively young, this process is still going on. Clustering is still occurring. Now, the first galaxies formed at about 500 million years, and the main process of galaxy formation continued for about another 100 million years. Okay, so as the gas clouds broke up within the galaxies, they formed into stars. And so the earliest stars detected are from about 2.5 billion years into the age of the universe. So things are kind of getting more gradual here. And it looks like star production peaked at about 5 billion years and has been dropping off ever since as the gas and other material in the galaxies becomes depleted. Now, as I said, most of the galaxies are spiral, but there are also what are called elliptical galaxies. Those galaxies are believed to have formed because smaller galaxies would collide with each other to form bigger galaxies. And what would happen is their rotational motion, what's called the angular momentum, would dissipate in the collisions. So while spiral galaxies are spinning faster and faster as the material comes in, kind of like an ice skater that brings his or her arms in, speeds up. Some galaxies, they would collide in such a way that would break up the rotation, and they would get this elliptical shape instead. Now, it turns out in elliptical galaxies, the gas for star formation is used up much more quickly than in spiral galaxies. Now, galaxies continue to grow into the present day. Just as clustering is still occurring, galaxies are still accreting material from the surrounding gas clouds. Now, I have a picture of some colliding galaxies over here. You can come up after the talk and look at them more closely. But these are downloaded from these are pictures taken by the Hubble Space Telescope. And a consequence of the way the galaxies formed and accreted due to irregularities in density is that galaxies appear to be concentrated along filaments. In other words, they're not uniformly distributed around the universe, but they're concentrated along sheets and filaments. And observations, this is actually a chart or a map of the distribution of galaxies in the immediate universe out to about 400 million light years, which is only a tiny fraction of the universe we can observe, but these measurements are very time consuming, so they're still in the process of doing these measurements. Now you'll notice that there's kind of a band here that's empty. This band is actually the plane of our galaxy where we just can't make observations because our galaxy is in the way. It's known as the zone of avoidance in astronomy. Okay, so now the galaxies have formed. Okay. Now, when galaxies formed, the core is assembled first. So that's where matter is densest in the cores of the galaxies. And so what happens is extreme high density of stars leads to a high rate of collision. So stars are colliding. And this in turn leads to objects that are so massive that gravity can't hold them up. And they turn into these giant black holes. And it's believed that in the center of pretty much every galaxy, there is a giant black hole, where the black holes can range in size from 2 million solar masses to 3 billion solar masses. A solar mass is the mass of our sun. We're a little, what should I say, egocentric. So we tend to define our units in terms of things close to home. So for example, the light year is defined in terms of the Earth's orbit or time to orbit the sun. The solar mass is defined in terms of the mass of our sun. I mean, it makes sense. There are things that are easy for us to measure. Okay. So now stars start to form, and stars generate their heat and light from nuclear reactions inside their cores, where they burn hydrogen into helium through the process of nuclear fusion. Now, when a star exhausts all of its hydrogen, it starts burning the helium into carbon, nitrogen, and oxygen. When it's exhausted the helium, it starts burning nitrogen, oxygen, and carbon into heavier elements until it gets to iron. Now, it turns out iron is the heaviest element for which you gain energy through nuclear fusion instead of having to expend energy. So iron is the end of the nuclear reaction chain inside stars. So when the star runs out of fuel, now it can no longer generate enough heat to hold itself up against the force of gravity. And there's a cataclysmic collapse in the core of the sun, which then bounces out and causes the star to explode, depending on the size of the star, into either a nova or a supernova. In the process of throwing supernova, the star will throw off most of its material. Sometimes over 90% of its material gets thrown into space. This material now is laden with all those heavy elements that formed during the nuclear fusion process. Plus, the energy of the supernova is so extreme that it forms all the other elements that we observe in the universe up through uranium, which is the heaviest element that has a reasonably long half-life that we can still observe it. Okay. Now, initially, the physics of how gas clouds collapse favored very large, short-lived stars. So these stars very quickly went supernova, throwing their material into space, and, if you will, contaminating space with all the heavy elements. Now, as more heavy elements formed in space, it turns out that the more heavy elements you have in the gas cloud, the harder it is for big stars to form, and instead you favor smaller and smaller and longer-lived stars. Now, I have a chart here, which is from one of my references, of what happens to stars as a function of their initial mass. Their lifetime here, their mass here, and inside what happens to them. For stars that are less than about 10 times the mass of the sun, they throw off most of their material, and then the core becomes what's called a white dwarf. For stars, let me get my numbers right. And for stars between 30 and 50 times the mass of the sun, the nucleus, the remaining remnant of the star is too big to be held up just by the force of atoms. So the electrons actually get pushed back into the protons, and the star becomes entirely neutrons. And that's called a neutron star. Now, if it's more than 50 solar masses, the remnant that's left behind is too big even for the neutrons to hold up, and it collapses into a black hole.
You might mention the black hole is called the Japanese so large.
Yeah.
There's no light.
Yes, it's called a black.
So we can't see.
Did everyone hear that?
Yeah.
It's called a black hole because the gravity is so great that nothing can escape, not even light. So they look black.
They're I think it's on radiation sometimes.
Well, as stuff falls in,
Stuff falls in.
it gives off radiation until it actually gets past the, what's called the event horizon, and the light can't get out anymore. Okay, back to our story. So now in spiral galaxies, currently about 3% of the gas is from, okay, spiral galaxies are currently now about 3% gas compared to the initial 100% gas. And most of that is from material thrown off by stars going nova, supernova, or just from the particles they give off called stellar wind from their normal operation. So now star formation is pretty much shut down compared to the early years. And even though there's still star formation going on, it's just a pale shadow of what it originally was. Okay, now I'll mention parenthetically, because we're egocentric creatures, that our solar system formed when the universe was about 10 billion years old. And as a medium-sized star, our sun is expected to burn for about another 5 billion years before it goes nova and becomes a white dwarf. Now, there are recent observations that indicate that the expansion of the universe may actually be accelerating. This appears to be due to a sort of negative gravity that's been called dark energy. And it appears to be due to some sort of potential energy in the actual fabric of space and time, what's called space-time. The acceleration seems to have begun about 5 billion years ago. Up until that time, the force of gravity was stronger than this dark energy. Then the universe reached a critical size, and the strength of the dark energy became greater than that of gravity. It should be noted, by the way, that this is not universally accepted by astronomers. It's one of the areas where we're still calling each other idiots in the literature. Now, a diagram discussing the discussion so far is over here, and I apologize for being so tiny. This was actually done by my old astrophysics professor at college. But if you come up close to the board afterwards, you might be able to read it. It appears they went out for lunch one day, and they went to an Italian restaurant. And one of them ordered pasta. Without thinking, his colleague ordered antipasta. And when the lunches were delivered, they annihilated him. Okay. So we future evolution. Okay. In 1996, a group of physicists at the University of Michigan performed a calculation on the future of the universe. What follows is highly speculative and strongly dependent on our current theoretical understanding of particle physics. I'll try to point to this really speculative stuff as we proceed. We currently live in what's called the Stelliferous Era, the period in which stars dominate the appearance and energy budget of the universe.